Hello, my name is Emanuel Casiano-Diaz, and today we are going to talk about how to quantify entanglement in fermionic systems. A many-body system is entangled if its constituents present correlations that cannot be described classically. In other words, by having information of subsystem A, you will automatically gain information about subsystem B without any classical mechanism conveying this information between the subsystems. Entanglement is a necessary resource for quantum computing, and that's why so many research groups are interested on it. In fact, this past summer, I attended a summer school on quantum science at Johns Hopkins in Maryland, and I got to use IBM's Quantum Experience, which is a quantum computer that they have remote access to, and you can play with it. So I think it's really cool that there are actual applications, like real applications for entanglement as of now. So let's start off by talking about the quantification of the entanglement and the different measures for it. But how does an entangled state even look like? Suppose I have a state psi that describes a system partitioned into subregions A and B. If this state psi cannot be written as a tensor product of the state of each subregion, then the state is entangled. Here is an example of an entangled state. Notice that there is no way for me to factor this state into the states of each subregion. If I were to measure region A and get blank circle as an outcome, I would automatically know that doing a measurement on B will yield the field circle state without me even having to measure B. On the other hand, if I know that A is in the field circle state, I automatically know that B will be on the blank circle state. This could have been a spin up, or this could have been spin down. This could have been a filled site on a lattice or a vacancy. Could be anything. On the other hand, an unentangled state will be able to be written as a tensor product of the states of each subsystem. In this example, notice that on both of these terms, A is on the field circle state, and here I have factored it out and written the whole state as a tensor product. Okay, so the actual quantification of the entanglement is obtained via the entanglement entropies. And these entanglement entropies, which are a thing of quantum information theory, have their origins in classical information theory through Shannon's entropy, which I have written here. Here, xi is some event that has a probability p of occurring. Shannon's entropy gives us a measure of how much information was gained by knowing the outcome of the event. Let's take a look at an example. Here I have a fair coin toss. In other words, there's probability 1/2 of landing tails and probability 1/2 of landing heads. By substituting p equals 1/2 into my Shannon entropy, I will get 1 at the end. This means I have gained a whole bit of information. If this coin had a probability of 0.7 to land tails, notice that the Shannon entropy will now be a smaller number. This happens because now I have more certainty of what outcome am I going to get before doing the coin toss. And an extreme case would be a coin with both sides tails. Here I know with probability 1, with 100% certainty what outcome am I going to get. So there is really no information gained. So the Shannon entropy is 0. So Shannon entropy will map out to quantum information theory as the von Neumann or the Rene entropies. Here, the row A represents the density matrix of subsystem A, and the probabilities are encoded in such density matrices. Okay, so now we have sort of a mathematical idea of how entanglement look like and how can we measure it, but how to measure it on a physical system. Let me tell you about the model that we have been studying. Okay, we first have to know that there are different ways to partition a many-body system. One of them is a spatial partition. So I could have some system in here. It's just a one-dimensional lattice separated into two spatially distinct regions. Here I have decided that my partition A will have a length of 3 sides, whereas the rest of the system, which is 4 sides, are going to be my B subregion. And I can measure the entanglement between these 2 subregions of our many-body system. Not only can we do a spatial partition, but we can also take a look at a system that is separated via a particle partition. Here, we don't even care about the spatial dimensions or the length of my space, the size of it. We have just decided to label some of the particles as being on our subset A, and the rest of the particles are our subset B. Okay, so the entanglement entropies, we have been calculating them on what is known as the TV model. I will get to why it's called like that later, but let me describe it to you. So this model depicts spinless fermions that are hopping on a one-dimensional chain under periodic boundary conditions. That means that the first side is connected to the last side. Not only that, but in this particular system, the contributions to the potential energy arise only from fermions that are neighboring to each other. So in this particular case, the fermion in this first side will not interact with the one in the third side, whereas the one in the third side interacts with the one in the fourth, and so forth. Okay, so this is the potential energy operator, where V is a tunable parameter, and N counts how many particles do I have inside A. Okay, so let's operate on this first lattice here. Notice that if I went to side 1, I would get a result of 0 when I count here. So no matter what I have on 2, which is the Ni plus 1, I will get a contribution of 0 to these 2. Okay, now let's move now to 2 and 3. So in 2 and 3, the particle number operator will return 1. So at the end, we get 1 as a result. And 3 and 4, and 4 and 1 will contribute nothing. So we have a contribution of V only. Let's take a look at the lattice beneath it. There's no neighboring fermions, so we have a contribution of 0. Okay, and I will not go through each of these, but just to take a look at a less trivial example, in this lattice on the top right of our slide, the contribution will be 3V because we have a V coming from the first pair of fermions that we see here in sides 3 and 4. Then we have another pair, and the third V comes from the fact that side 1, remember that is connected to side 4, so essentially they are neighboring also. Using a similar argument, we can build a kinetic energy operator, but we would have to move into K space, K being the wave vector. After we have built our kinetic energy operator in K space, we can apply a discrete Fourier transform to find its representation in real space. So notice how here at the bottom line I have moved from K space to I space. I just being a label of what site are we on. Also, notice a new operator, two new operators that are introduced here, which is the C dagger and the C. C dagger creates a fermion on side I, while C destroys a fermion on side I. We can add these two operators to build the Hamiltonian operator, which is awesome because if I have my Hamiltonian operator, I can act on some state to get the eigen energies as a result. And if I have the eigenenergies, I can build their corresponding eigenstates. In particular, we're interested in the ground state, the TV model. Okay, so here I have written down the recipe to get the entanglement in the TV model. First of all, we need to define our system. Here I said that we're going to have a TV model chain with 4 sides, 2 particles, and the particle partition being of size 1 only, meaning that we have 1 particle on sub-region A, while all the remaining particles, which in this case is also 1, are going to be our subset B. Once we define the system, since we have our Hamiltonian operator, we can build a matrix representing the operator by sandwiching this operator based on all possible states. Once we have the Hamiltonian matrix, we diagonalize to find the eigenvalues. The eigenvalue that'll give us our ground state is obviously the minimum eigenvalue, which will give us the ground state energy, from which we can obtain our ground state psi. Once we have psi, we can take the outer product with itself to build the density matrix corresponding our many-body system. But if you remember, the entanglement entropies are written in terms of the reduced density matrix of one of the subsystems, in this case A. So we have to take the partial trace of the density matrix of the whole system with respect to B to throw away all degrees of freedom of subregion B and have only the information of A. And once we have the reduced density matrix, we just plug and chug into our entanglement entropy equations to get the values. Before continuing to the actual results we have gotten already, I would like to illustrate how quickly does the dimensions of the Hamiltonian matrix grow with system size. Notice that by the time that we want to simulate 16 fermions, we will have a Hamiltonian with dimensions 10 to the 9 times 10 to the 9. In other words, it'll have roughly 10 to the 18 entries. And this is very costly memory-wise. In fact, to get the 16 fermions, we need to have roughly 800 gigabytes of RAM, which we have done. But this is our limit as of now. Okay, so now I would like to show you some of the results we have gotten for particle entanglement of our spinless fermions. Previous work 2 hours suggested this form for the finite size scaling of the entanglement entropy in the TV model. The first term corresponds to the contribution to the entanglement entropy of coming from free fermions. And these other 2 terms are what we set out to find in one of our projects. We want to observe what is the interaction dependence of these terms. Or moreover, we want to look at the interaction dependence of the A and gamma of this exponent gamma. Okay, so here we have a plot of the entanglement entropy with the contribution coming from the free fermion subtracted, because remember, we want to observe the interaction dependence of those other two terms, the A and the gamma exponent. Here below, we can see a phase diagram of the TV model. So the TV model is known to be a phase-separated solid for infinitely attractive interaction strengths. In other words, the fermions cluster together. On the infinitely repulsive regime, we get a charge density wave. That means that we will have a fermion, then a vacancy, then a fermion, then a vacancy, or the other way around. We could have started with a vacancy, doesn't matter. While between -2 and 2, we have a Luttinger liquid. We successfully found this gamma exponent and discovered that it was dependent on the Luttinger parameter. You have the actual expression here, which at the same time depends on the interaction strength. I forgot to write A here, but we were also able to get it by doing a fitting of some other plot that I am not showing here. But I just want to show that we were actually successful in proving the form for the particle entanglement in the TV model. And we have a published paper which you are encouraged to check out. So what are we doing now? Now we are taking a look at what is known as the operational entanglement. The operational entanglement is a measure of entanglement that was proposed in the early 2000s by Howard Wiseman and Jon Vaccaro, which takes into account things such as particle number superselection rule. In other words, that particles have to be conserved when we do a measure on our system. So this operational entanglement is a more physically accurate measure. And that's why we're interested on it right now. Here is an example of the results we have started to gather. Here I am showing the operational entanglement corresponding to the von Neumann and the second order Rényi entropies for a site, also in the TV model, for a lattice, that has 28 sites, 14 particles, and a spatial partition of 14. Notice how we can see very clearly the phase transitions that I talked about earlier at -2 and +2. And here is the result, but for 16 fermions. Notice the lower density of data points due to the fact that it is so expensive memory-wise to get these results. But at least they seem to have the same shape, so we're good. Or hopefully we are. Not only that, but we have also started to get analytical results for what this operational entanglement will converge to in the infinitely attractive and infinitely repulsive regimes. So what's left to do? What I want to do is implement my own version of the Langsos diagonalization, which is the algorithm we are using to get the eigenvalues from our Hamiltonian matrix. And there's really nothing groundbreaking about this. I just want to do it for the pedagogical for pedagogical purposes only, just to know in more excruciating detail what this is all about. So you know these results about operational entanglement that I showed you, we want to write a paper and hopefully submit it by February. And last but not least, I want to submit and defend my thesis by March. So that's what's left, and I would like to thank you all for your attention, and please feel free to ask me any questions that you may have. Thanks.